Welcome to note set number 38, where we'll be talking about continuous time convolution, which is a tool for finding the zero state response. So this is directly analogous to what we saw for discrete time. So this is just an alternate way of thinking about how the system behaves, thinking in the time domain rather than in the frequency domain. And just like for discrete time, and like we saw earlier for continuous time, if we hit the system with a delta function, the thing that comes out is called the impulse response, and we reserve the symbol h of t to mean the thing that comes out from putting in a delta function, or the impulse response. And this is done under the assumption of all the initial conditions being equal to 0. And as we have said before, we can show that the impulse response is nothing more than the inverse Laplace transform of the transfer function, and also the inverse Fourier transform of the frequency response. So the transfer function and the impulse response form a Laplace transform pair. The frequency response and the impulse response form a Fourier transform pair. And so since these two things, transfer function and frequency response, tell us how the system behaves and allows us to analyze the system, we would think that the impulse response h of t should also be able to be used to tell us how the system behaves and be able to analyze the system in terms of it. So the convolution property of both the Fourier transform and the Laplace transform tell us how this comes about. So let's say we've got an input signal x of t, and we've got its Fourier transform and or its Laplace transform. And if we've found the frequency response or the transfer function of the system, we do an inverse transform to get this thing called the impulse response. Okay, so we've got that. Yeah, so that should be y of t, not y of n. What we've been doing is saying, okay, form the product and do the inverse transform, and we get the output. What the convolution property of these transforms say is that the equivalent to forming the product and doing the inverse is this operation called convolution. And for discrete time, it was defined in terms of a sum. And for continuous time, it's defined in terms of this integral. But if you compare the structure of this integral to the structure of that convolution sum for the discrete time case, you'll see that they look very, very similar. And therefore, you can carry over a lot of your insight from discrete time into continuous time. So what this is saying is, if we've got an input x of t, we've got a system with an impulse response h of t, which we found by somehow doing this inverse transform, then all we have to do is do this integral to find what the output is. So understanding how this integral behaves and how to think about it, how to visualize it, is a key step to understanding how systems work. So what this integral is telling us is that if you want to know, say, the output for t equal to 2, you're going to have to replace 2 here, do the integration over all time, or all tau values, and you'll get a number, and that number is the output at time 2. Now, obviously, to find the output at all time, we'd have to do this integral over and over and over, and in fact, it seems at an uncountably infinite number of points, which seems to be troubling. But we'll see that at least for simple scenarios where we want to visualize what's happening in a simple circuit or a simple system, we can find some tricks to get around some of those issues. Okay, so I'm just restating here the general convolution result, and we can simplify that when our system is causal, or when the input is causal, or both. So let's first look at the case where the system is causal. And so what that means is h of t is equal to 0 when t is less than 0. So we look at this thing in here in our integral, it's h of t minus tau, so we need to know at what point is that going to be 0 and cause the entire integrand to be 0. So h of t minus tau is equal to 0 whenever its argument is 0. So when t minus tau is less than 0, and that means whenever tau is greater than t. So as we're integrating over tau, as soon as we get tau up to value of t, we stop. So again, if I were to put in 2 there, I would only have to integrate up to 2, not to infinity. So that's when I have a causal system. My impulse response is 0 for negative t. Similarly, if I have a general LTI system, not necessarily causal, but my input is causal, meaning that it's equal to 0 for t values prior to 0, then what ends up happening is, as I'm integrating over tau, I don't have to go to negative tau values because the integrand would be equal to 0 over that range. So I can start integrating at 0. And then the scenario that's most likely to show up in the cases that someone would have to analyze would be the case where the system is a causal system and the input doesn't start being non-zero until t equal to 0. And then we have both of these. We start at 0 and we stop at t. So now we have an integral over a finite range, which is a little easier to deal with. Now, just like we had for the discrete time case, we have some properties, and the first 3 that I list here are identical to the discrete time case. So you might want to go back and review that and see how that works. So commutativity, associativity, distributivity, we talked about in detail for the discrete time case, so you should go back and revisit those. Now, a couple new ones. The derivative property. The derivative property says that if I convolve x of t with v of t first, and we can really think of v of t as an h of t if we want to. So if I find the output of a system and then I take the derivative, it's the same as first taking the derivative and then putting it into my system. Or alternatively, differentiating the impulse response and then putting building a new system with that impulse response and putting my original signal in. So these are things that just help us mathematically analyze different cases of systems. And similarly, we have an integration property that says if I convolve x and h and to get an output, and I were to take the running integral of that output, I could find that in one of 2 alternate ways. I could either first take the running integral of the input and run it through the system, or I could define a new impulse response by first taking the running integral of the system's impulse response, build that system, and put my original signal in. So these are just some little properties that help us deal with different scenarios that crop up. To be honest, in this course we're not going to deal with those too much, but for subsequent courses you may encounter those kinds of things. Now, just like we did for discrete time, we're going to walk ourselves through the steps of doing convolution graphically. So this is very similar to what we saw for discrete time, so I'm going to go through it a little bit faster. The only real catch here is that instead of adding up a bunch of numbers like we do for discrete time, you have to actually do an integral. So there's a little bit of difference here, but the basic idea is the same. So we're going to rewrite the signals as a function of tau. We're going to flip one or the other of them, either one which makes sense. Notationally here I'm going to flip h of tau, and then to help us set up our integrals and figure out where we integrate from and to, I've come up with this idea of finding the edges of these flipped signals. So we'll have this so-called left-hand edge after we've flipped it. We'll have the right-hand edge, and this 0 part of the subscript that I'm using is just saying that it's after we've flipped but before we've done any shifting. Then we're going to shift. So we're going to shift by an arbitrary value of t, and we're going to find its edges. Now, it's no surprise that edges of something that hasn't been shifted the edges of the thing that are shifted are just shifted versions of those edges, so that's no big deal. So that just means that the shifted edge on the left will always just be the unshifted left edge with t added to it. And likewise, the right-hand edge is also just with t added to the non-shifted right-hand edge. So if the signal that you flip is not finite duration, you could have an edge that is either minus infinity and or plus infinity. So you'll have to keep track of that. Then in order for us to figure out what we're integrating and where we have to integrate it, we have to find these different ways that these shifted signals overlap. So I call that find the regions of tau overlap. And we'll work through some examples to help you understand how to do that. And when we're doing that, these regions should be contiguous. There should be no gaps. There should be no time interval left unaccounted for. Now, once we find these regions, then we have to form the product that we're going to integrate. And again, a lot of this will become clearer as we go through an example, so I'm going to skip through a lot of this. And then finally, we have to assemble the output. So let's go through an example. It might help for you to keep those steps off to the side as we go through this example. So here's the two signals that we're going to convolve. We've got an x of t, we've got an h of t. First step, pretty easy. Just write everything in terms of tau. That's just notational issues. Now we're going to flip one, and I usually find it easier to flip the shorter signal. So in this case, this one is shorter, so I flip that. So I anchor it here. I anchor it at 0, regardless of where the signal is, and I flip it about the vertical axis. Now I'm going to find the edges of the flipped but not shifted signal. So in this case, the right edge is at 0 and the left edge is at -1. And then this is just motivating the next step. I'm going to skip this because I think it's pretty clear that, you know, if I shift a signal, its edges just get shifted by t. But you can work through those two examples to show that that definitely does hold true. So when I shift this thing, my edges were at -1 and 0. Now my edges are at t-1 and t. So this is just a way of figuring out, once I specify a certain amount of shift, so if I'm going to shift, say, by 2, where are these edges on my tau axis? Well, if I shift by 2, it's going to be at 2-1, and it's going to be at 2. So 2-1 is 1. 2 is 2, so this would really be over here at 1 and 2. So this is just a way of arbitrarily writing a shifted signal without really committing to where it really is going to be. And obviously, as I change t to arbitrary values, this thing moves back and forth to different positions. Okay, step number 5, I have to find the regions of tau overlap. So I'm doing this on the tau axis, and I want to know, so for different regions of t, how do these two shifted things interact and overlap? So for this example, I declare that there's a region 1, which I call no tau overlap. So since this edge is always at t, as soon as I let t be less than 0, this edge will be to the left of that edge, and the pulses will have no overlap. So in other words, when I form the product, I get 0. Okay, so region number 1 is all values of t less than 0. Region number 2 I'll call partial tau overlap on the way in. I don't say that explicitly here. And so what I want there is I only want partial overlap, so I want this edge to be in the middle of the pulse somewhere, and I want this edge to be in the middle of that pulse. So I don't want neither one to be completely inside the other. So that will happen whenever t, for this example, is greater than 0, but t minus 1 is less than 0. So that boils down to this interval. Notice that when I finish region 1, I start region 2. There's no gap. Let's go on to region 3. Region 3, for this case, because I'm shifting the shorter signal, there's going to be a point where it's completely inside. So I call this total tau overlap. So that edge is inside, the top one, that edge is inside. And so I need, again, two conditions for that to happen. I need t minus 1 to be greater than 0, but I want t to be less than 2. So if I write those two conditions, I find that those are equivalent to this interval. So again, remember, region 2 stopped at 1, and region 3 starts at 1. Region 4, for this example, is partial tau overlap on the way out. So I want this edge to be in the middle here. So I want t minus 1 less than 2. I want t to be bigger than 2, and that leads to this interval. And again, notice that when I finish region 3, I'm starting region 4. And then finally, for this example, region 5, no tau overlap on the out, going out of the pulse. For that case, I want t minus 1 to be greater than 2. And so that leads to t greater than 3. So again, notice when region 4 ends at 3, region 5 starts at 3. So I now have 5 regions. How many regions I have and what they'll look like depends upon the structure of the signals. So you kind of have to practice this a little bit to learn all the ins and outs of it. Step 6 is for each one of these regions I need to form the product and figure out what the integral is. So remember, region 1 was t less than 0. So t less than 0 means this edge is always to the right of this edge. And so under that case, the product, there's no non-zero parts that overlap, so the product is equal to 0. When I integrate that product, I'm integrating 0, so I get 0. So what I've just found out is that the output is equal to 0 for all negative t. That's nice. So now I've just figured out an entire swath of output values. Notice how I don't have to do this for every single individual t. I only have to do it within each region. And that's the whole point of the regions. Region 2, remember, was for the case of 0 to 1. And so in that case, this edge is inside, but this edge is outside. So when I form the product, it's just going to be these parts interacting. So for this example, when I form that product, I get this little rectangular pulse. Its height is equal to 6. That's just 2 times 3. And where does it exist? It exists from 0, which comes from here, out to t, which comes from that edge. So that's the thing that I need to integrate. So what do I need to integrate? 6, because that's the value of it here. And where do I need to integrate? From 0 to t. So from 0 to t. So there's the integral that I need to do. And remembering your little bit of rules from calculus, you'll find that you get an integral value of 6t. So now over this interval of t, my output follows that function. Region 3 exists for this range of t. And for that range of t, if you remember, this edge was in, this edge was in. So when I form the product, the only parts that are going to matter are the parts between here. Again, I have 2 times 3 gives me a rectangular pulse of height 6, but it only exists from t minus 1 up to t. So the edges here limit the region of integration. So now I'm going to integrate 6 from t minus 1 up to t. And when I do that, I get a value of 6. So it's constant over that interval. Region 4, from 2 to 3, That's the case where this edge is in and this edge is out. So I form the product. It's this little rectangle. Again, height of 6. But what sets the edges of this? That edge sets here, and this edge sets there. So now I only have to integrate from t minus 1 to 2. And so I integrate 6 over that range, and I get something that looks like this. And so that's what the output looks like over that interval. And then finally, region 5 was for t greater than 3. That means this edge is outside of that edge, always to the right of it. The product is 0. I'm integrating 0. I don't even have to worry about what my limits of integration are. My output is 0 for all of that. And so now putting all of these together, we found that for t less than 0, the output was 0. Then we found that for t between 0 and 1, the output followed the function 6t. So that's a straight line, intercept of 0, slope of 6. So it goes from 0 to 1 up to 6. Then we saw that in region 3, for t values from 1 to 2, the output signal stays constant at 6. And then for region 4, which is 2 to 3, we see that it follows this minus 6t plus 18. And that looks something like that. And then y of t is equal to 0. So notice I've got every value of t accounted for. There's none missing. I'm going from all of the t's down to minus infinity, through here, through here, through here, and then all the values up to plus infinity. And notice that there are no gaps. I go up to 0, I start at 0 to 1, start at 1 to 2, start at 2 to 3, 3, and ever more after that. So we'll do some examples of this in class. Come prepared, having gone through this example, and be ready to do some convolution. In a bigger picture viewpoint, these are things that help you understand how to think about how a system behaves and operates in the time domain. So engineers need to be able to switch back and forth between these. By far, the frequency domain is the more powerful way of analyzing systems, but you need to know about the time domain. Thanks. I'll see you in the next video.